3I Atlas is defying everything we know about celestial visitors. As it hurtles closer to Earth, the comet is doing the unthinkable. It's fading, dimming, vanishing before our eyes. This mysterious visitor from beyond our solar system challenges the fundamental laws that have guided comet science for centuries. Instead of growing brighter with each approach, it slips quietly into darkness, leaving astronomers around the globe baffled and racing to decode its secrets. How does that happen? How can something racing toward you lose its brilliance instead of blazing brighter? It's like watching a mystery unfold in real time across the canvas of space, and every astronomer with access to a telescope is scrambling to understand what they're witnessing. This isn't supposed to happen. Comets follow rules. They obey the physics we've studied for centuries. When they approach our world, when they draw nearer to the warmth and energy of our cosmic neighborhood, they light up. They become spectacular. They throw off tails of gas and dust that stretch millions of miles behind them, glowing like celestial torches. But 3I Atlas is breaking those rules right in front of us. Stay with me, because in the next minutes, we're going to uncover exactly why 3I Atlas is fading fast as it approaches Earth, and what this strange behavior tells us about the nature of interstellar visitors and the secrets they carry from distant star systems. Think about what that means for a moment. This object didn't form in our solar system. It wasn't born from the same cloud of dust and gas that created our sun, our planets, everything familiar to us. It came from somewhere else entirely, shaped by forces and conditions we can only imagine, carrying chemistry and structure from a place we've never seen. And now, as it makes its closest pass by Earth in December of this year, it's behaving in a way that challenges our understanding. Is it crumbling? Is the structure breaking apart under invisible stresses? Could there be something about its composition, something fundamentally different from the comets we know, that makes it respond to our solar system's environment in unexpected ways? You can feel it, can't you? That pull of curiosity, that itch in your mind that wants answers. The same feeling that kept ancient humans staring at the night sky, wondering what those points of light meant. We're hardwired to seek patterns, to solve puzzles, to understand the universe around us. And right now, 3I Atlas is presenting us with a puzzle that doesn't have an easy answer. Scientists are working around the clock, pointing every available instrument at this fading visitor, trying to capture data before it slips too far away. Amateur astronomers are setting up their equipment in backyards and on rooftops, adding their observations to the global effort. Everyone who looks up at the sky with curiosity is part of this investigation. The stakes feel higher because this isn't just any comet. Interstellar objects are rare. Before 2017, we had never confirmed a single visitor from beyond our solar system passing through our neighborhood. Then came Oumuamua, that strange cigar-shaped object that sparked endless debate and speculation. After that, we spotted Borisov, which looked and behaved more like the comets we're familiar with. And now, 3I Atlas. Each one teaches us something new about what exists out there in the vast spaces between stars. Each one is a messenger carrying information about alien solar systems, about how planets and comets form under different suns, about the diversity of the universe beyond our tiny corner of existence. But this fading, this unexpected dimming as it approaches hits different. It feels wrong. It triggers an instinctive unease, like watching something that should be alive slowly losing its light. Is it dying? Can a comet die? These aren't questions we normally ask, but 3I Atlas is making us reconsider everything. Some unverified whispers online have suggested patterns in the dimming, rhythms that seem too regular to be random. Claims of pulses, like a heartbeat echoing from the depths of space. Scientists have been quick to point out that these claims lack solid evidence, that what we're seeing appears to be natural comet behavior even if it's unusual. But the speculation persists because humans need stories, need explanations, need to fill the gaps in our knowledge with something, even if it's just possibility. Here's what we know for certain. 3I Atlas made its closest approach to the Sun back in late October, swinging through perihelion and absorbing massive amounts of solar energy. That's when comets typically put on their best show, when the ice and frozen gases on their surfaces heat up and explode into space, creating those magnificent glowing comas and sweeping tails. And 3I Atlas did brighten during that time, just as expected. Observers around the world watched it intensify, saw its coma expand, tracked the development of its tail. Everything seemed normal. Everything followed the script we've seen countless times before with other comets. But then something changed. As it swung past the sun and started heading outward again on its trajectory, as it simultaneously moved toward its closest approach to Earth in mid-December, the brightness started dropping, not just leveling off, but actively decreasing. Measurements showed the light output falling week after week, the glow becoming more subdued, the comet becoming harder to spot even with good equipment. And that's where the mystery deepens, because while the comet is moving away from the sun, which would naturally reduce its brightness, it's getting closer to Earth. From our perspective, from our viewing angle, it should still appear prominent. The geometry should work in our favor. Yet it's fading. This is the hook that has captured the attention of the global astronomical community. This is why forums are buzzing with theories, why data is being shared and analyzed faster than ever, why professional and amateur observers alike are losing sleep to catch every possible glimpse. Something is happening up there, something we don't fully understand yet, and the window to study it is closing. 3I Atlas won't stay close forever. It's already on its way out, moving on the outbound leg of its journey through our solar system, and soon it'll be too faint and too distant for most telescopes to track effectively. The clock is ticking, and every observation matters. If this cosmic mystery has grabbed your curiosity the way it's grabbed mine, do me a favor right now. Hit that like button. It tells me you're invested in this investigation, that you want to explore these deep questions about our universe together. And drop a comment below telling me where you're watching from, as this space drama unfolds in the sky above you. Are you in the northern hemisphere where 3I Atlas is visible in the pre-dawn hours? Are you in the southern hemisphere watching from a different angle? Let's build this community of curious minds, all looking up at the same mysterious visitor, all wondering what secrets it's hiding in its fading light. Because what comes next in this story is going to challenge everything we thought we knew about how interstellar objects behave when they pass through our neighborhood. Let's rewind the clock just a bit, back to when 3I Atlas first reappeared in our skies after its dangerous dance with the Sunday. There's something almost mythical about that moment when a comet emerges from behind our star, when it breaks free from that blinding glare and becomes visible again to observers on Earth. It's like watching a ship return from a storm, battered perhaps, but still sailing. And for astronomers who had been tracking 3I Atlas before it disappeared into the sun's glare, that reappearance was a moment of genuine excitement. Would it have survived the intense heat and radiation? Would it still be intact? Would it be brighter, more active, throwing off more material as its ices continued to sublimate in the solar warmth? The answer at first seemed to be yes, as October turned to November and 3I Atlas climbed higher in the pre-dawn sky. Telescopes around the world locked onto it and began taking detailed measurements. The comet sported a visible coma, that fuzzy cloud of gas and dust surrounding the nucleus, and a tail that stretched behind it like a cosmic banner announcing its presence. Spectroscopic analysis revealed the expected signatures of sublimating ices: water vapor, carbon dioxide, carbon monoxide, all the usual suspects we see when frozen volatiles heat up and transform directly from solid to gas. Everything looked normal. Everything suggested this interstellar visitor was behaving like any well-mannered comet should. But here's where the first hints of strangeness began to creep in. Some observers noted that the coma, while prominent, didn't seem to be growing at the rate they expected. After perihelion, after that closest brush with the sun's energy, comets usually experience what we call an outburst, a sudden, dramatic increase in activity as fresh ice becomes exposed and explosively sublimated. It's like uncorking a bottle that's been shaken. The pressure releases all at once and creates a spectacular show. Astronomers were watching for that outburst from 3I Atlas, preparing their instruments to capture it in detail, ready to analyze what happens when an interstellar comet gets superheated by our Sunday. But the outburst never came. Or if it did, it was so subtle that it barely registered above the baseline activity level. Instead, what observers saw was a kind of steady state, a plateau where the brightness and activity seemed to stabilize rather than spike. That was unusual but not unprecedented. Sometimes comets surprise us. Sometimes the surface develops a crust of non-volatile material that insulates the ice underneath, preventing explosive activity. Sometimes the spin rate or orientation of the nucleus affects how the sublimating gases escape. There are dozens of variables that can influence comet behavior, and not every comet reads the same textbook. So the astronomical community watched and waited, taking measurements, comparing notes, building up a dataset that would help them understand this particular interstellar visitor's personality, and that's when the dimming began to show up in the numbers. Subtle at first, just a few percentage points here and there that could have been attributed to measurement uncertainty or atmospheric conditions. But as more observers contributed their data, as the measurements accumulated over days and then weeks, a pattern emerged that couldn't be dismissed. 3i Atlas was losing brightness, not just fluctuating, which would be normal, not just going through temporary dips due to rotation or localized activity changes. It was on a consistent downward trend, getting fainter with each passing night. You have to understand what a strange feeling that creates for people who study these objects. Comets are supposed to follow predictable patterns based on their distance from the Sun and their intrinsic activity levels. We have models, mathematical frameworks, that describe how brightness should change as a comet moves along its orbit. These models aren't perfect. Comets are complex, chaotic objects that can throw curveballs, but they work well enough most of the time to give us solid expectations. And those expectations for 3i Atlas said that even as it moved away from the Sun after perihelion, it should remain reasonably bright through its close approach to Earth in December. The Earth-comet distance was going to reach a minimum, which should have made it a great observing opportunity, a chance for even small telescopes and binoculars to spot this rare interstellar visitor. But instead, the reports kept coming in with lower magnitude numbers, indicating decreasing brightness. Astrophotographers who had captured beautiful images of 3i Atlas in early November were finding it harder to pull out detail in mid-November. Visual observers who had easily spotted it with binoculars were needing larger aperture telescopes to find it. Something was changing, and changing faster than the models predicted. The journey this comet was taking through our solar system was not following the expected script. Think about that journey for a moment. This object spent thousands or millions of years drifting through interstellar space, through the cold and dark between stars where temperatures hover just above absolute zero. Out there, it was frozen solid, every molecule locked in place, dormant and unchanging. Then it entered our solar system, fell into the Sun's gravitational well, and began to heat up for the first time in ages. The ices started to sublimate. The nucleus began to shed material. The comet woke up from its long sleep and started to transform, responding to our star's energy in ways that were shaped by its composition, by whatever mixture of ices and rock and organic compounds it carried from its birth system. That transformation should have continued, should have intensified as it swung through perihelion, and then maintained significant activity as it climbed back out of the inner solar system. But it didn't. Instead, 3i Atlas seemed to be quieting down, pulling back, dimming like a fire that's running out of fuel even though it shouldn't be. Was the surface composition unusual? Did this interstellar comet have less ice than expected? Or was the ice locked away beneath a layer of material that wasn't allowing it to sublimate effectively? These questions started to dominate the discussions at observatories and in online astronomy forums. Everyone who was tracking the comet could see the same trend, and everyone was puzzling over what it meant. The timing added another layer of intrigue. Here was 3i Atlas, approaching Earth for what should have been the viewing opportunity of the year for an interstellar object, and it was fading just when it should have been at its most impressive from our perspective. It felt almost cruel, like the universe was dangling something fascinating in front of us and then pulling it away before we could fully appreciate it. Amateur astronomers who had been planning observing sessions, who had been telling friends and family to watch for this cosmic visitor, found themselves adjusting expectations. Outreach events at planetariums and science centers had to recalibrate their presentations. The story of 3i Atlas was not going to be the triumphant tale of a bright, easily visible interstellar comet gracing our skies. It was going to be something more subtle, more mysterious, more frustrating in its refusal to behave as expected. And yet, that very unpredictability is part of what makes this so compelling. We live in an age where we can predict eclipses centuries in advance, where we can calculate the orbits of distant planets with incredible precision, where the clockwork of the cosmos seems well understood. But then something like 3i Atlas comes along and reminds us that the universe still has surprises, that there are behaviors and phenomena we haven't fully catalogued yet, that every new object we study has the potential to teach us something, to expand our understanding, to show us aspects of nature we hadn't anticipated. The dimming of 3i Atlas wasn't just a disappointment for observers hoping for a spectacular show. It was a puzzle, a scientific mystery that demanded explanation, and that mystery was about to deepen even further as more powerful instruments turned their attention to this fading visitor. When something strange happens in space, when an object starts behaving in ways that challenge our expectations, that's when the big guns get rolled out. And by big guns, I mean the most powerful telescopes humanity has ever built, instruments that can peer across vast distances and tease out details that would be invisible to lesser equipment. 3i Atlas, with its unexpected dimming, quickly became a target of interest for some of these premier observing platforms. Scientists who had been allocated time on major telescopes began incorporating this interstellar visitor into their observation schedules, recognizing that this was an opportunity to study something genuinely unusual, something that might not come around again in our lifetimes. The Hubble Space Telescope, that venerable orbital observatory that has revolutionized our understanding of the universe over more than 3 decades of operation, turned its gaze toward 3i Atlas. Hubble has a unique advantage for comet observations. It sits above Earth's atmosphere, which means it doesn't have to contend with atmospheric turbulence and distortion. The images it captures are sharp, detailed, pristine. When Hubble looks at a comet, it can resolve features in the coma, track the evolution of the nucleus, monitor how jets of material shoot out from active regions on the surface. For 3i Atlas, these capabilities were exactly what scientists needed to try to understand the dimming behavior. The images that came back were fascinating and perplexing in equal measure. Hubble captured the comet at multiple points during its post-perihelion journey, creating a time series that allowed researchers to watch how the object evolved. What they saw was a coma that appeared to be fluctuating in size and density. At times it looked robust and well-defined, suggesting healthy outgassing from the nucleus. At other times, it seemed more diffuse and faint, as if the activity had decreased. This kind of variation isn't completely unusual for comets. They can go through cycles of activity as the nucleus rotates and different regions face the sun, but the overall trend still pointed toward declining activity, toward an object that was becoming less energetic over time. There were also observations from the Psyche spacecraft, which was launched to study a metal-rich asteroid, but has instruments capable of capturing images of other solar system objects when opportunities arise. During its cruise phase, Psyche made observations of 3i Atlas from a different vantage point than Earth-based telescopes, providing additional data that helped triangulate the comet's properties. These observations revealed interesting structure in the coma, hints of jets or streamers of material emanating from specific regions of the nucleus. Jets like these are direct evidence of active sublimation, specific spots on the comet's surface, where ice is vaporizing and shooting gas and entrained dust particles out into space. But here's what made the observation so puzzling. Even though these jets were visible, even though there was clear evidence of ongoing activity, the overall brightness of the comet continued to decline. That's a contradiction that doesn't fit neatly into our standard models. If material is actively leaving the nucleus, if sublimation is happening, the comet should be putting energy into that process and reflecting and scattering sunlight from all that released gas and dust. The brightness should be maintained or even increased. Instead, 3i Atlas was fading, suggesting that either the rate of activity was decreasing faster than expected, or that something about the composition of the material being released wasn't contributing to brightness the way we usually see. As the comet continued on its trajectory toward its closest approach to Earth in mid-December, the observing campaign intensified. Telescopes around the world coordinated their efforts, creating a network of observers that could track 3i Atlas continuously as it moved across the sky. Professional observatories with large aperture instruments captured high-resolution spectra, breaking down the comet's light into its component wavelengths to identify what molecules were present in the coma. Amateur astronomers with smaller but often very capable equipment contributed photometric measurements, tracking the overall brightness and how it changed from night to night. Even observers with just binoculars or small telescopes added their reports, helping to build a complete picture of how visible the comet was under different conditions. This collaborative approach is one of the beautiful things about astronomy. When something interesting happens, the entire global community comes together to study it, sharing data freely, comparing notes, building knowledge collectively. Professional and amateur observers work side by side, each contributing what they can, all driven by the same curiosity and wonder about the universe. For 3i Atlas, this cooperation was essential because the comet's dimming meant that every observation was precious, every data point mattered. As it grew fainter, fewer instruments would be able to detect it, which meant the window for study was closing. What emerged from all these observations was a complex picture of an object that wasn't behaving consistently. Some nights, 3i Atlas would show slightly enhanced activity, a small bump in brightness that suggested an outburst or increased sublimation. Other nights, it would be quieter, fainter, less prominent. The variability suggested that the nucleus was rotating, exposing different surface compositions to sunlight as it spun, which would naturally create fluctuations in activity. But superimposed on that variability was the overall downward trend, the persistent dimming that couldn't be explained by rotation alone. Spectroscopic observations added another layer to the mystery. The composition of the coma, the mix of molecules being detected, was generally consistent with what we see in other comets. Water vapor dominated, as expected, since water ice is the most common volatile material in comets. Carbon dioxide and carbon monoxide were present in reasonable amounts. There were hints of more complex organic molecules, which is always exciting because it tells us about the prebiotic chemistry that exists in these frozen objects. But nothing in the composition screamed unusual or abnormal. 3i Atlas looked, chemically speaking, like a fairly typical comet, which made the dimming behavior even more puzzling. At this point, some unverified claims began circulating online, as they often do when something in space captures public attention. Some observers claimed they were seeing regular patterns in the brightness variations, pulses or cycles that occurred at suspiciously consistent intervals. The suggestion, sometimes stated explicitly and sometimes just implied, was that these patterns might indicate something artificial, some kind of signal or structure that wasn't natural. These claims spread quickly through social media and various forums, generating excitement and speculation among people who were following the story of 3i Atlas. But here's where scientific rigor becomes crucial. When claims like these emerge, they need to be examined carefully, tested against the data, subjected to peer review and independent verification. And when scientists did exactly that with the supposed patterns in 3i Atlas's brightness, they found that the evidence didn't hold up. The variations that observers were seeing could be explained by natural processes, rotation of the nucleus, changes in viewing geometry, fluctuations in sublimation rates, even the effects of Earth's atmosphere on ground-based observations. There was no compelling evidence of artificial regularity, no signal that couldn't be accounted for by the complex but entirely natural behavior of a comet responding to solar heating. This is an important moment to pause and appreciate how science works. It's tempting to jump to exciting conclusions, to see patterns, and assume they mean something profound. Our brains are wired to find patterns, even when they're not really there. A tendency called pareidolia that served our ancestors well when they needed to spot predators in the bushes, but can lead us astray when we're looking at noisy astronomical data. Science requires us to be skeptical, to demand evidence, to rule out ordinary explanations before we consider extraordinary ones. And in the case of 3i Atlas, the ordinary explanation that this is a natural comet going through natural processes, even if those processes are producing unexpected results, remained the most consistent with all the available data. That said, the ordinary explanation still left big questions unanswered. Why was the dimming so pronounced? Why wasn't the activity maintaining the brightness we expected? What was different about this interstellar visitor compared to comets that formed in our own solar system? These questions didn't require appeals to artificial structures or alien technology. They were simply questions about comet science, about physics and chemistry, and how these ancient objects respond to their environment. And as December approached and 3i Atlas continued its journey, those questions became more urgent because the opportunity to find answers was slipping away with each passing night, just as the comet itself was fading from view. By early December, there was no denying it anymore. The numbers were too consistent, the observations too numerous, the trend too clear. 3i Atlas was dimming significantly, losing brightness at a rate that exceeded what any reasonable model of post-perihelion comet behavior would predict. Observers who had been tracking the comet since its reappearance documented a drop in magnitude that represented a substantial decrease in the amount of light reaching Earth from this object. And remember, in astronomy, magnitudes work backwards. A higher number means dimmer, a lower number means brighter. So when the magnitude measurements for 3i Atlas kept increasing week after week, that was direct evidence of fading. What made this particularly striking was the context. The comet was simultaneously approaching its closest distance to Earth. The geometry of the situation should have worked in observers' favor. Even if the intrinsic activity of the comet was decreasing as it moved farther from the Sun, the fact that it was getting closer to us should have compensated to some degree. Think about it like a light bulb. If the bulb is getting dimmer but also getting closer to you, those two effects partially cancel out, and the light you actually see might stay relatively constant. But with 3I Atlas, the dimming was so pronounced that it overwhelmed the effect of decreasing distance. The comet was getting harder to see, even as it was getting closer, which is exactly backwards from what every instinct tells us should happen. Textbooks and introductory astronomy courses teach the principle clearly. As a comet approaches, it brightens. As it recedes, it dims. This is comet behavior 101, the most basic expectation we have. And yet here was 3I Atlas, defying that basic expectation in front of hundreds of observers around the world. It created a cognitive dissonance, a sense that something was fundamentally wrong with the picture we were seeing. Like watching water flow uphill or seeing a dropped object fall upward instead of down. The universe wasn't breaking its rules. Of course, the rules of physics remain inviolate, but something about this comet's specific situation was producing a result that looked wrong to our expectations. Scientists scrambled to gather as much data as possible while the comet was still within range of sensitive instruments. Every clear night became precious. Telescope time that had been allocated for other projects was sometimes redirected toward 3I Atlas because the opportunity to study an interstellar object exhibiting unusual behavior doesn't come around often. Observatories in different parts of the world coordinated their observations to maintain continuous coverage as Earth rotated, ensuring that the comet was always being monitored by someone, somewhere. The data piled up: photometric measurements, spectroscopic analyses, high-resolution images, all of it contributing to a growing picture of an object in transition, changing in ways that challenged understanding. And it wasn't just professional facilities that were documenting the dimming. Amateur astronomers, whose contributions to comet science are often invaluable, were reporting their observations through established networks like the Comet Observation Database and various regional astronomy groups. These observers, working with equipment ranging from high-end amateur telescopes to modest instruments that might cost less than a decent camera, provided ground truth for what was visible to the broader community. Their reports confirmed what the professionals were seeing with bigger telescopes. 3I Atlas was becoming a challenging object to observe, requiring darker skies and more aperture than it should have needed at this point in its apparition. Some of these amateur observers brought decades of experience to their observations. They had tracked countless comets over the years, knew what to expect, understood the typical progression of brightness as a comet moves through the inner solar system, and many of them expressed surprise, even concern, at what they were seeing with 3I Atlas. This wasn't normal behavior. This wasn't a pattern they recognized from years of comet watching. The shared sense among experienced observers was that something about this interstellar visitor was different. Something about its response to our solar system's environment wasn't following the familiar playbook. The question that haunted every discussion, every analysis session, every conference call among researchers was simple: why? Why was 3I Atlas fading so dramatically? What mechanism could account for this behavior? Was the nucleus breaking apart, fragmenting under thermal or tidal stresses, reducing the active surface area and thus the outgassing rate? That's a known phenomenon with comets. They can split or crumble, especially if they're structurally weak or have spent little time in the inner solar system before. But if 3I Atlas were fragmenting, we should be seeing evidence of it in the images. There should be multiple nuclei or a spread out, diffuse appearance that indicated the object was coming apart. And for the most part, the images didn't show that. The nucleus appeared to be intact, singular, holding together. Could it be a surface effect? Perhaps the outer layers of the nucleus had developed a dark, non-volatile crust that was insulating the ice underneath, preventing further sublimation. This happens with comets. Sometimes they essentially seal themselves off, creating a shell of dehydrated material that reduces activity dramatically. If that were happening with 3I Atlas, it might explain the dimming. But usually, crust formation is accompanied by specific signs: a very dark, low albedo surface, minimal or no gas production, a dramatic drop in activity that happens relatively quickly. And while 3I Atlas was indeed dimming quickly, there was still evidence of ongoing sublimation, still jets and structures in the coma that suggested at least some parts of the surface remained active. Another possibility involved the composition of the nucleus itself. Maybe 3i Atlas was simply running low on volatiles. Perhaps this interstellar comet didn't have as much ice as a typical solar system comet of similar size. If it formed in an environment where ice accretion was less efficient, or if it had undergone previous passes near other stars during its interstellar journey, it might have been depleted of its most volatile materials before it even entered our solar system. What we were witnessing might be the exhaustion of its available ice, the final gasp of sublimation before the comet became dormant and inert. That would be a significant finding. It would tell us something important about the conditions in other planetary systems and how comets there compare to ours. Geometry played a role too, of course. The angle at which we viewed the comet, the orientation of its tail, the scattering properties of the dust in the coma, all of these factors influence how bright a comet appears from Earth. As 3i Atlas moved along its orbit and our viewing geometry changed, some of the dimming could be attributed to these optical effects. Light that was being scattered in one direction earlier in the apparition might now be scattered in a different direction, away from Earth. The dust grain size, distribution, the composition of the particles, the density of the coma, all of these variables affect how efficiently the comet reflects and scatters sunlight back toward us. But even accounting for all the geometric factors, even building models that incorporated every known variable, the dimming remained more extreme than predictions. There was a gap between what the models said should be happening and what observers were actually seeing. And that gap is where the real science happens, where discovery lives. When observations don't match predictions, it means either our models are incomplete or our understanding needs refinement. It means there's something new to learn, some factor we haven't properly accounted for, some piece of the puzzle we're missing. Russian observatories, with their long tradition of comet observation and their geographic coverage that fills gaps for Western facilities, contributed crucial data during this period. Observers in Siberia and other regions were able to track 3i Atlas during times when it was below the horizon for American and European telescopes, maintaining continuity in the dataset. Their reports confirmed the global picture. The dimming was real, consistent across all observers regardless of location or instrument type. This wasn't an artifact of any single telescope or observing site. It was a genuine change in the comet's brightness, a physical phenomenon that demanded physical explanation. Picture it this way. Imagine you've planned a reunion with an old friend, someone you haven't seen in years. You arrange to meet at a specific place and time. You're anticipating this moment, building it up in your mind, and then they arrive, but they're not quite as you remembered. They're quieter, more subdued, different somehow from the person you expected to see. That's what the astronomical community was experiencing with 3i Atlas. This was supposed to be the big reunion with an interstellar visitor, a chance to study something from beyond our solar system up close and in detail. But instead of the bright, active comet everyone had hoped for, 3i Atlas was arriving dimmed and mysterious, presenting more questions than answers. The scientific papers were already being written, data was being analyzed and organized for publication, but those papers would take months to go through peer review and appear in journals. In the meantime, the story was unfolding in real time in the observations, in the nightly reports from telescopes, in the discussions happening in online forums and at professional meetings. Everyone watching knew they were witnessing something unusual, something that would be studied and debated for years to come. And as mid-December approached, as the date of closest approach to Earth arrived, the anticipation was mixed with a tinge of melancholy. This was likely to be the best chance we'd ever have to study 3i Atlas. After it passed Earth and continued outbound, it would grow fainter and more distant until even the most powerful telescopes couldn't track it anymore. The window was closing, and the mystery of its dimming remained unsolved, hanging in the sky like the comet itself, fading but not yet forgotten. Behind every observation, every data point, every image of 3i Atlas, there are people, real human beings who have dedicated their lives, or at least significant portions of their time, to understanding the universe. These are the astronomers, professional and amateur, young and old, working at major observatories or in their own backyards, who form the global community of sky watchers. And when something like 3i Atlas comes along, when the universe presents a puzzle that demands attention, these people respond with a passion and dedication that goes beyond mere professional obligation. This becomes personal. This becomes a quest. Think about what it means to be an observational astronomer working on a time-sensitive project like this. You're often working at night, obviously, because that's when the stars are visible. You're contending with weather that doesn't care about your observation schedule. Clouds roll in, atmospheric seeing degrades, equipment malfunctions, You're competing for telescope time with other researchers who have their own important projects. You're analyzing data that can be noisy and difficult to interpret, trying to extract signal from background, trying to make certain of what you're seeing before you report it to the broader community. It's challenging, often frustrating work that requires both technical skill and stubborn persistence. And yet, when something genuinely interesting appears, when an object like 3I Atlas enters the picture, all of those challenges become secondary to the opportunity. Suddenly, you're not just collecting data on another celestial object, you're pursuing something unique, something that might only pass through our neighborhood once in human history. That knowledge drives people to extraordinary efforts. Professional astronomers juggle observation proposals, collaborate with colleagues across multiple institutions, stay up through the night monitoring telescope operations. Amateur astronomers bundle up against winter cold, haul equipment to dark sites away from city lights, spend hours guiding their telescopes and capturing images that might reveal just one more detail about this mysterious visitor. The story of 3I Atlas's observation campaign is really the story of these hunters in the dark, these dedicated individuals who pointed their instruments skyward and refused to let this comet fade without a fight. Some of them captured images that revealed subtle structures in the comet's tail, wispy features that hinted at how solar wind was interacting with the outflowing gas. Others focused on photometry, meticulously measuring brightness night after night to document the dimming curve with precision. Still others pursued spectroscopy, analyzing the chemical fingerprints left in the comet's light, building up a profile of what this interstellar visitor was made of. There were moments of frustration, certainly. Nights when the weather refused to cooperate, when forecasts promised clear skies but clouds rolled in anyway. Technical problems that cropped up at the worst possible times. A tracking error that ruined a long exposure. A software glitch that corrupted data. Equipment that chose precisely the wrong moment to fail. These are the realities of observational astronomy, the unglamorous challenges that every observer faces. But they persist because the alternative, missing the opportunity, letting the comet pass unstudied, is unacceptable to someone who has devoted themselves to exploring the cosmos. Among the observations that generated discussion were reports of interesting variations in the tail structure. Some images appeared to show twists or kinks in the tail, places where the flow of material seemed to be disturbed or redirected. These features can be caused by the magnetic fields embedded in the solar wind. As the wind flows past the comet, it drapes around the coma and can create complex structures. They can also be influenced by changes in the comet's activity level, by sudden releases of material that create denser regions in the tail, by the rotation of the nucleus changing, which active areas are exposed to sunlight. Interpreting these features requires careful analysis and comparison with models of how comet tails develop and evolve. Then there were the observations that captured what appeared to be discrete ejection events, moments when the comet seemed to release a puff or plume of material that expanded outward into the coma. These events are fascinating because they give us insight into what's happening on the surface of the nucleus. Something triggered that release, perhaps a pocket of volatile ice became exposed, or a cliff face on the nucleus collapsed and revealed fresh material underneath, or temperature changes caused structural failure in the nucleus. Each ejection event is like a window into the comet's interior processes, a glimpse of the dynamics happening on this small, distant object. Some of the online speculation about 3I Atlas seized on these variations and structures, interpreting them as evidence of something unusual or even artificial. Claims circulated that the timing of certain events was too regular, that there were patterns suggesting control or purpose rather than random natural processes. These claims spread quickly through social media and enthusiast forums, taking on a life of their own and generating considerable discussion and debate. It's a pattern we've seen before with other unusual celestial objects. When something doesn't immediately fit our expectations, there's a segment of the public that jumps to extraordinary explanations. But here's what the careful, methodical analysis by professional scientists showed. The features observed in 3I Atlas's coma and tail were consistent with natural comet behavior. The variations could be explained by the rotation of the nucleus, by the uneven distribution of active regions on the surface, by changes in solar wind pressure, by viewing geometry effects. When researchers looked for the supposedly regular patterns that were being claimed, they found that the timing wasn't actually regular at all. It just appeared that way if you cherry-picked certain data points and ignored others. This is a classic example of confirmation bias, where people see what they expect or hope to see rather than what's actually there. NASA and other space agencies were quick to address these claims, issuing statements that clarified what the data actually showed and emphasizing that there was no evidence of anything artificial or anomalous beyond the natural behavior of a comet. They reminded the public that comets are complex objects with many variables affecting their appearance and behavior, and that unusual doesn't mean alien or artificial, it just means we're seeing something we need to better understand. The scientific community appreciated these clarifications because misinformation can spread rapidly and create confusion that makes it harder to communicate actual discoveries. The passion these observers brought to the campaign was matched by their willingness to share their findings openly. Data flowed into public databases almost as quickly as it was collected. Images appeared on websites and social media, allowing anyone interested to follow along with the investigation. Amateur astronomers wrote blog posts describing their observations and what they'd learned. Professional researchers gave public lectures and participated in online discussions, making themselves accessible to anyone curious about the comet. This openness is a hallmark of the astronomical community, a recognition that the universe belongs to everyone and that discoveries should be shared broadly rather than hoarded. What emerged from this collective effort was a rich, detailed dataset on 3I Atlas that captured its evolution during the critical weeks around Earth's closest approach. This dataset will be analyzed for years to come, mined for insights that might not be apparent in the immediate aftermath of the observations. Future researchers will return to these images and measurements, bringing new tools and new perspectives to the question of why this interstellar comet behaved the way it did. The hunters in the dark did their job. They captured the data, documented the phenomenon, preserved the record. Now the next phase could begin, making sense of it all, building the explanations that would turn observations into understanding. Here's where the story takes a turn toward resolution, where the scientific process begins to provide answers to the mystery that had been building. Because as much as the dimming of 3I Atlas seemed strange and inexplicable, as much as it violated expectations and generated speculation, the reality is that nature always has reasons for what it does. Physics doesn't break down just because we're confused. The universe operates according to consistent principles, and when we observe something unexpected, it means we need to look deeper, think more carefully, and apply our understanding more rigorously to the specific circumstances at hand. The explanation for 3I Atlas's dimming, when it finally crystallized through analysis and modeling, turned out to be rooted in factors that scientists had understood in principle, but perhaps hadn't fully appreciated in the specific context of this comet's trajectory. Let's break it down piece by piece, because the answer is both simpler and more nuanced than you might expect. First, consider the comet's relationship with the Sunday. 3I Atlas passed through perihelion, its closest point to the Sun, back in late October. That's when it received the maximum energy input, when solar radiation was most intense, when the heating was strongest. And as expected, that's when the comet was most active. Sublimation rates were high, the coma was well developed, brightness peaked. But here's the crucial point. After perihelion, as the comet moved away from the Sun on its outbound trajectory, that energy input decreased rapidly. The Sun's influence drops off with the square of distance moved twice as far away, and you receive 1/4 of the energy. Move 3 times as far, and you get 1/9. As 3I Atlas receded from perihelion, the solar energy available to drive sublimation decreased week by week. The ices on the surface received less heat. The sublimation rate dropped. Less gas flowed out into the coma, which meant less dust was lifted off the nucleus, which meant the coma became less dense and less efficient at scattering sunlight. All of this led directly to decreased brightness. This is normal, expected behavior for any comet moving away from the Sunday. The unusual aspect with 3I Atlas was how dramatic this decline was relative to the modest increase in distance. The comet seemed to be turning off quickly, more quickly than typical comets do in similar situations. But there's a second factor that's equally important: viewing geometry. While 3I Atlas was approaching Earth and would reach its closest point to our planet in mid-December, the angle at which we viewed the comet was changing continuously. The orientation of the tail, the scattering angle of sunlight off the dust in the coma, the phase angle, all of these geometric factors influence how bright a comet appears from Earth. And for 3I Atlas, the geometry was working against us as it approached. The comet wasn't coming straight at Earth. It was approaching at an angle, and the way the coma scattered light at that angle meant less light was being directed toward our vantage point than there would have been at other orientations. Think of it like watching a car's headlights. If the car is coming straight toward you, the lights appear bright because you're looking directly at the source. But if the car is passing at an angle, if you're off to the side, those same headlights appear dimmer, even though they're putting out the same amount of light. The light is just going in a different direction relative to your viewing position. With 3i Atlas, we were increasingly viewing the comet from an angle where the scattering of sunlight by the coma particles wasn't optimized to send light toward Earth. This geometric effect compounded the intrinsic dimming from decreased activity. Now add a third factor, the possibility of uneven outgassing. Comets aren't uniform objects. The nucleus is likely to have regions with different compositions, some areas richer in volatiles than others. As the nucleus rotates, and comet nuclei typically rotate with periods ranging from a few hours to a few days, different areas get exposed to sunlight. Active regions rich in ice produce strong outgassing when they face the sunday. Inactive regions, covered perhaps with dust or depleted of volatiles, produce little activity even when illuminated. If 3i Atlas had a rotation that was bringing less active regions into sunlight as it moved outbound, that would contribute to the observed dimming. The comet wouldn't be uniformly decreasing in activity. Rather, the active spots would be pointing away from the sun more of the time, reducing the average output of gas and dust. When you combine all three of these factors, decreased solar energy input post-perihelion, unfavorable viewing geometry, and uneven outgassing from a rotating nucleus, you get exactly what observers were seeing. A comet that was dimming significantly even as it approached Earth. Each factor individually might account for a modest decrease in brightness, but acting together, they created a compound effect that resulted in the pronounced fading documented by observers worldwide. The mystery wasn't that physics was breaking down or that something impossible was happening. The mystery was that this particular combination of circumstances was creating a more extreme result than simple models had predicted. This is actually a beautiful illustration of how science works at its best. Faced with an anomaly, with observations that didn't match expectations, researchers didn't throw up their hands or jump to wild conclusions. They dug deeper. They refined their models. They incorporated more variables and ran more detailed simulations. They examined the specific orbital mechanics of this comet, the specific geometry of this encounter, the specific properties suggested by the spectroscopic data. And through that careful, methodical work, a coherent explanation emerged that accounted for what was being seen without requiring any exotic physics or unprecedented phenomena. And this is important, even as this explanation came together, it raised new questions. Why was the post-perihelion decline in activity so steep for 3i Atlas? Was there something about its composition that made it particularly sensitive to decreasing solar input? Did it have less ice than a typical comet, or was the ice distributed differently throughout the nucleus? These questions point toward deeper investigations, toward the kind of detailed analysis that requires more data, more observations, more time spent poring over the measurements and extracting every bit of information they contain. That's where instruments like the James Webb Space Telescope come into play. Webb, with its infrared capabilities, can probe aspects of comet composition that visible light telescopes can't access. It can detect thermal emission from the nucleus itself, providing information about temperature and surface properties. It can analyze the molecular composition of the coma with exquisite sensitivity, identifying species that might be present in small quantities, but tell us important things about where the comet formed and what conditions were like in its birth system. There have been discussions about targeting 3i Atlas with Webb during its apparition, scheduling observations that could provide that next level of detail. The challenge is that telescope time on facilities like Webb is incredibly precious and highly competitive. Every minute of observation has to be justified, has to promise significant scientific return. For 3i Atlas, the case is strong. Interstellar objects are rare, opportunities to study them are fleeting, and the unusual behavior of this particular comet makes it scientifically compelling. But whether observations ultimately happen depends on scheduling constraints, competing priorities, and the difficult decisions that allocation committees have to make about how to use limited resources. The astronomical community hopes for additional high-quality data, but has to be prepared for the possibility that what's already been collected might be all we get. In the meantime, there's relief mixed with the lingering questions. Relief because the observations do make sense within the framework of known physics. There's no need to invoke anything exotic or unexplained. The dimming of 3i Atlas, while more pronounced than initially expected, is understandable given the specific circumstances of this encounter. That's satisfying in a fundamental way. It reinforces that our understanding of comets, while not perfect, is generally sound. The models work when we apply them carefully and account for all the relevant factors. But the wonder persists. Even understood, even explained, 3I Atlas remains a remarkable object. It's still an interstellar comet, still a visitor from beyond our solar system, bringing with it chemistry and structure shaped by an alien environment. It still has stories to tell about how comets form around other stars, about what the interstellar medium is like, about the diversity of planetary systems in our galaxy. The fact that its dimming can be explained doesn't make it any less fascinating. If anything, understanding the mechanism deepens the fascination, because now we can ask more targeted questions, can design better observations for future interstellar visitors, can refine our expectations based on what we've learned from this encounter. With the primary mystery of the dimming explained, at least in broad strokes, we can step back and appreciate the fuller picture of 3I Atlas as an object of study. Because the brightness wasn't the only interesting thing about this comet. Far from it, throughout its passage through the inner solar system, 3I Atlas displayed a range of phenomena that captured attention and provided valuable data about comet physics and the nature of interstellar objects. Let's explore some of those other aspects, the features and behaviors that went beyond the central narrative of the fade, but were no less scientifically important. One of the most visually striking elements of any comet is its tail, or more precisely, its tails, plural, because comets typically develop two distinct tails that point in different directions and are caused by different physical processes. There's the dust tail, composed of small, solid particles that are lifted off the nucleus by the sublimating gases and then get pushed away from the sun by radiation pressure, the physical force exerted by sunlight itself. This tail is often broad and curved, following the comet's orbital path, because the dust particles retain some of the comet's original velocity as they separate from the nucleus. Then there's the ion tail, composed of electrically charged molecules that get swept away by the solar wind, the stream of charged particles constantly flowing outward from the sunday. The ion tail is typically narrower and straighter than the dust tail, pointing almost directly away from the sun because the solar wind is so fast and energetic that it dominates the motion of these charged particles. 3I Atlas displayed both types of tails, and careful observations revealed some fascinating structure. The dust tail showed variations in brightness and width along its length, suggesting changes in the rate at which dust was being ejected from the nucleus. Brighter regions in the tail indicated periods of enhanced activity when outbursts or increased sublimation had lifted more dust into the coma. Fainter regions corresponded to quieter periods. By mapping these variations and accounting for the light travel time, the fact that different parts of the tail represented dust ejected at different times in the past, researchers could reconstruct a timeline of the comet's activity level over the preceding weeks. The ion tail showed its own interesting features. At times, it appeared to develop disconnections, places where the tail seemed to break or separate from the coma, with a segment of tail drifting away while a new tail grew in its place. These disconnection events are known to occur when changes in the magnetic field structure of the solar wind interact with the comet's ionized coma. Essentially, magnetic field lines that were connected to the coma get severed, and the ions that were following those field lines get carried away as a detached structure. Then new field lines connect to the coma, and a fresh ion tail develops. It's a dramatic demonstration of the dynamic nature of the solar wind and how it interacts with comets. Some observers also reported seeing what appeared to be jet-like features emanating from specific points in the coma. These jets are direct evidence of active regions on the nucleus surface, places where sublimation is occurring, where gas is streaming out into space and carrying dust particles along with it. The jets can appear as bright streaks or fans in images, and their orientation and strength provide information about where the active areas are located on the nucleus and how they're oriented relative to our viewing direction. For a rotating nucleus, jets can create spiral patterns in the coma as the active regions sweep around, painting trails of material that gradually expand and fade. There have been suggestions, based on some of the imagery, that 3I Atlas might have shown evidence of ice volcanism, a phenomenon where volatile materials beneath the surface suddenly find a path to escape, creating explosive eruptions that throw material outward. This is different from the steady sublimation that normally drives comet activity. It's more violent, more sudden, like a geyser going off. Some comets do show evidence of these kinds of events, particularly when heating from the sun reaches ice deposits that have been insulated beneath a surface layer, causing pressure to build up until something gives way. If 3I Atlas experienced ice volcanoes, that would be an exciting finding because it would tell us about the internal structure of the nucleus, about layering and composition variations beneath the surface. Now, it's important to note that identifying ice volcanism with certainty is challenging. You need high-resolution observations that can clearly distinguish a sudden ejection event from the background activity of the comet. You need to rule out other explanations like impacts from small meteoroids, which can also create brief outbursts, or structural failures where part of the nucleus collapses. The evidence for ice volcanoes on 3I Atlas is suggestive but not yet definitive. It's one of those areas where additional analysis of the existing data, and possibly future observations of similar objects, will help clarify what we're seeing. Another fascinating aspect of the 3I Atlas story involves the spacecraft encounters. While there was no dedicated mission to intercept the comet, planning and launching a spacecraft on short notice to rendezvous with a fast-moving interstellar object is beyond our current capabilities. Several spacecraft in the inner solar system happened to have sightlines to the comet or passed through regions of space where they could sample its environment indirectly. The Europa Clipper mission, en route to Jupiter to study that moon's subsurface ocean, made observations of 3I Atlas from its unique vantage point. The Parker Solar Probe, which makes close passes by the Sun to study solar wind and the Sun's corona, potentially passed through regions where solar wind had recently interacted with the comet's ion tail, carrying away material that could be detected by the spacecraft's instruments. These kinds of in-situ measurements, even if they're opportunistic rather than planned, can provide information that's impossible to get from remote observations with telescopes. They can tell us about the composition of the ion tail with much greater precision, about the structure of the plasma environment around the comet, about how solar wind parameters change when they encounter a comet's extended atmosphere. The data from these spacecraft encounters will be analyzed and compared with the ground-based and space-based telescope observations to build a more complete picture of 3I Atlas and its interaction with the solar environment. All of this additional data, the tail structures, the jets, the possible ice volcanism, the spacecraft measurements contributes to our broader understanding of comets, and particularly of interstellar comets. Every detail we can extract from observations of 3I Atlas becomes a data point in the larger catalogue of what we know about these objects. And that catalogue is still quite small when it comes to interstellar visitors. We've only confirmed a handful of them passing through our solar system. Each one is precious from a scientific standpoint, because each one represents a sample from a different corner of the galaxy, a snapshot of conditions and compositions that exist around other stars. One of the most important questions astronomers want to answer is how similar or different interstellar comets are from solar system comets. Do they have the same basic composition, roughly equal parts ice and rock, with a mixture of simple and complex organic molecules? Or are there systematic differences, perhaps reflecting different formation conditions around stars with different masses or metallicities? Do they behave the same way when they encounter the Sun? Or are there structural differences that affect how they respond to heating? The spectroscopic data from 3I Atlas, showing familiar molecules like water, carbon dioxide, and carbon monoxide, was reassuring in one sense. It suggested that comets are comets regardless of where they form, that the basic chemistry is universal. But the unusual dimming behavior reminds us that we can't take anything for granted, that each object needs to be studied individually to understand its specific properties. Looking forward, the observations of 3I Atlas will inform how we approach future interstellar objects. We'll know to pay closer attention to post-perihelion activity, to model the viewing geometry more carefully, to anticipate that dimming might be more pronounced than simple models predict. We'll have better templates for what kinds of behaviors to expect, which will help us distinguish between normal variation and genuinely anomalous activity if we encounter an object that truly is behaving strangely. This is how science progresses incrementally, through the accumulation of case studies and examples, through the gradual refinement of models and expectations. And there's something poignant about the educational value of 3I Atlas for amateur astronomers and the general public. Despite the dimming, despite the fact that it didn't become the bright, naked-eye spectacular that would have made headlines and captured global attention, this comet provided an opportunity for thousands of people to participate in real science, to contribute observations, to follow along with an unfolding cosmic story. Astronomy clubs organized viewing sessions. Educators incorporated 3i Atlas into their curricula. Online communities tracked the comet's progress and shared images and reports. For many people, this was their first exposure to the concept of interstellar objects, their first awareness that things from beyond our solar system do occasionally pass through our neighborhood. That educational and inspirational value shouldn't be underestimated. It's part of how we build a scientifically literate society, how we foster the next generation of researchers and explorers. Now we shift from the scientific analysis to something more personal, more immediate, your opportunity to participate in this story yourself. Because 3i Atlas, despite its fading, remains visible from Earth for those with the right equipment and the determination to find it. This is your chance to point your own eyes, your own telescope or binoculars, at a genuine visitor from another star system. Think about that for a moment. This isn't a solar system comet that's been orbiting our sun for billions of years. This is something that formed elsewhere, that traveled through the interstellar void, that carries with it the signature of an alien planetary system. And you can see it. You can be part of the observation campaign, can add your own data point to the global effort to understand this object. Let's talk practically about how to observe 3i Atlas during its current apparition. As of mid-December, the comet is moving through the constellation Virgo in the pre-dawn sky. For observers in the northern hemisphere, that means looking toward the eastern horizon in the hours before sunrise, when the sky is dark but before twilight has begun to brighten the background. The comet's dimming means you'll need optical aid binoculars at minimum, but preferably a telescope with some aperture to gather more light. A 6-inch or larger telescope is ideal, though experienced observers with excellent dark skies might spot it with good binoculars if they know exactly where to look. The key is preparation. Don't just go out and sweep the sky hoping to stumble across the comet. Use one of the many astronomy apps or planetarium software packages available to determine exactly where 3i Atlas is located for your date, time, and location. These tools will show you the comet's position against the background stars, which constellations it's moving through, what its altitude above the horizon will be at different times of night. Plan your observation session for when the comet is highest above the horizon. Low altitude means you're looking through more atmosphere, which dims and distorts the view. The darker your sky, the better your chances. So if you can get away from city lights and find a truly dark location, do it. The difference is dramatic. When you locate the area of sky where the comet should be, scan slowly with your telescope or binoculars. You're looking for something fuzzy, something that doesn't quite look like a star. Stars, even through a telescope, remain point sources of light. Comets, by contrast, have extent they show up as diffuse patches, often with a brighter central condensation where the nucleus is located and a fainter surrounding coma. The tail may or may not be visible depending on the comet's activity level and your equipment. With 3i Atlas's current dimness, you might see only the coma itself, a ghostly smudge against the star field. But that smudge is what you're after. That faint glow is photons that left the comet and traveled across space to reach your eye or your camera sensor. You're directly observing something from beyond our solar system. If you're able to photograph the comet, even better. Astrophotography has become remarkably accessible with modern digital cameras and processing software. You don't need exotic equipment, a DSLR or mirrorless camera on a tracked mount, or even just a smartphone held up to a telescope eyepiece can capture images of brighter comets. For a dim object like 3i Atlas, you'll need longer exposures and careful processing to pull the comet's signal out of the background noise, but the technology is well developed and there are extensive online resources and communities that can guide you through the process. Every image you capture contributes to the historical record of this comet's passage. Decades from now, researchers might return to the collected images from December and find details that weren't apparent in the initial analysis. And here's something important. Report your observations. There are established networks and databases where amateur astronomers contribute their comet observations, and this data genuinely matters. Professional researchers use it. It helps establish the light curve, the record of how brightness changes over time with more frequent data points than professional telescopes alone can provide. It confirms the positions and helps refine orbital calculations. Your observation, combined with hundreds of others, becomes part of the collective scientific understanding of 3i Atlas. You're not just a passive consumer of astronomy information, you're an active participant in the research process. But beyond the scientific contribution, there's something deeply personal about observing a comet. It connects you to a tradition that stretches back thousands of years, to the earliest humans who looked up and wondered about the moving lights in the sky. Comets have always held a special place in human consciousness. They're transient, ephemeral visitors that appear and then vanish, unlike the fixed stars and predictably wandering planets. Ancient cultures saw them as omens, as messages from the gods, as harbingers of change. We know better now. We understand what comets are physically, but they still stir something primal in us. They remind us of the dynamic, ever-changing nature of the cosmos. They're evidence that the solar system isn't a static clockwork, but a place where new things can and do arrive, where the unexpected happens. Observing 3I Atlas in particular carries an extra layer of meaning because of its interstellar origin. When you see that faint smudge through your eyepiece, you're looking at matter that formed around another star. The water ice in that nucleus condensed from gas in a protoplanetary disk that orbited a sun that isn't ours. The organic molecules in the comet were created by chemistry that happened light years away, in conditions that may have been similar to our early solar system, or may have been quite different. This comet is a sample from the broader galaxy, a tiny piece of the universe beyond our immediate neighborhood that happened to pass close enough for us to study. Share your experience, post your observations online, join discussions in astronomy forums, talk to friends and family about what you've seen. Astronomy is often portrayed as a solitary pursuit, the lone observer under the stars, but it's actually an incredibly social endeavor. The global community of people who care about the sky, who get excited about comets and eclipses and meteor showers, is vast and welcoming. Your enthusiasm and your observations are part of what keeps that community vibrant and growing. And when you share your experience of observing 3I Atlas, you're helping to spark interest in others who might not have realized they could participate, who might not have known that something so remarkable was visible if they just knew where to look. Consider keeping an observing log. Write down not just the scientific details, date, time, instrument used, seeing conditions, magnitude estimate, but also your impressions, your thoughts, how it felt to see this interstellar visitor with your own eyes. These personal reflections become part of your own scientific journey, a record you can look back on years from now and remember this specific moment when 3I Atlas was passing through. Astronomy has a way of marking time, of creating memories attached to specific cosmic events. People remember where they were and what they saw during memorable celestial occurrences. This could be one of those memories for you. And if the weather doesn't cooperate, if clouds block your view or circumstances prevent you from observing directly, you can still participate through the wealth of images and data being shared online. Follow the hashtags related to 3I Atlas on social media. Check the websites of major observatories to see their latest images and press releases. Read the observing reports that people post to astronomy forums. The virtual participation is different from direct observation, but it still connects you to the event, still makes you part of the global audience witnessing this comet's passage. In our interconnected age, you don't have to be physically at a telescope to be involved in the story. As 3I Atlas continues its outbound journey through December and into early spring, it will keep fading, becoming more and more challenging to observe. Eventually, even large professional telescopes will lose it against the background stars and galaxies. But for these precious weeks and months, it's still within reach. It's still observable, still yielding data, still offering that connection between observers on Earth and a visitor from the depths of space. Make the effort if you can. Bundle up against the cold pre-dawn air, set up your equipment, and spend some time searching for that faint fuzzy patch. When you find it, when you see 3I Atlas for yourself, you'll have joined an experience that spans the globe, that connects you to professional scientists and amateur enthusiasts alike. All of you looking at the same remarkable object and wondering about its origin, its journey, and the secrets it might still reveal. So here we are, nearing the end of this journey through the story of 3I Atlas, this interstellar comet that captured attention not by being brilliant and spectacular, but by being mysterious and challenging, by defying expectations and forcing us to think more carefully about what we understand. As I write this, the comet is continuing its outbound path, moving away from both Earth and the Sun, fading ever deeper into the darkness from which it came. Soon it will be beyond the reach of all but the most powerful telescopes. Eventually, it will leave our solar system entirely, returning to the interstellar void, traveling on a trajectory that will carry it through the galaxy for millions of years before it might, by chance, encounter another star system. Think about that trajectory for a moment. Before entering our solar system, 3I Atlas was in interstellar space for an unimaginable length of time. We can calculate backward along its orbit and estimate where it came from, what part of the galaxy it was moving through before the sun's gravity began to affect it. Current analyses suggest it approached from the general direction of the constellation Ursa Major, but tracing its path further back becomes increasingly uncertain. It could have been ejected from its home system recently, astronomically speaking, or it could have been wandering between stars for millions of years. It might have had previous close encounters with other stars that altered its path, or it might have been on a relatively straight trajectory through the sparse matter of interstellar space. What we do know is that its encounter with our solar system is brief. A few months of visibility, a few weeks when it was bright enough for detailed study, and then it's gone. The speed at which interstellar objects move through our neighborhood, typically tens of kilometers per second, relative to the sun means they don't linger. They're here, and then they're not, like cosmic travelers passing through a way station without stopping. For 3I Atlas, perihelion marked the turning point, the moment when it swung around the sun and began heading back out. Earth's closest approach in mid-December was our best viewing opportunity, the moment when the comet was nearest to us even as it was already moving away from the Sunday, and now both of those milestones have passed. What remains is the outbound journey, the gradual return to the cold and dark. But the data remains, the observations persist. The thousands of images captured by telescopes around the world, the spectroscopic measurements documenting the chemical composition, the photometric curves tracking the brightness changes. All of that information is preserved, archived, available for analysis and reanalysis for as long as we maintain our scientific records. This is one of the beautiful aspects of modern astronomy. Unlike centuries past, when observations existed only in handwritten logs and drawings, today's digital data can be stored indefinitely and accessed by researchers anywhere in the world. Future scientists, perhaps working decades from now with analysis techniques that don't yet exist, will be able to revisit the 3I Atlas dataset and potentially extract new insights that we're missing today. The James Webb Space Telescope, if observations of 3I Atlas are ultimately scheduled and executed, could provide a capstone to the observation campaign. Webb's infrared capabilities would reveal thermal properties of the nucleus, would detect molecules in the coma that are invisible to optical telescopes, would measure isotopic ratios that tell us about formation conditions in the comet's birth system. These observations, if they happen, will be analyzed intensely, compared with the earlier data from Hubble and ground-based telescopes, and synthesized into the most complete picture we can create of what 3I Atlas is and where it came from. Even if Webb observations don't occur, if scheduling constraints or other priorities prevent it, the existing dataset is still scientifically rich and will support research for years to come. One of the questions that will continue to be debated is the one we've focused on throughout this story. Why did 3I Atlas dim so dramatically during its Earth approach? We've explored the likely answers: decreased solar heating post-perihelion, unfavorable viewing geometry, uneven outgassing from a rotating nucleus. But scientific explanations are rarely final. They're working hypotheses, models that fit the available data, but remain open to revision if new information emerges. As the full dataset is analyzed in detail, as researchers dig deeper into the photometric curves and spectral features, it's possible that nuances will emerge that require refining the explanation. Maybe there was indeed a compositional factor that made this comet more sensitive to decreasing solar input than typical comets. Maybe the nucleus structure, perhaps a loosely bound aggregate rather than a solid chunk, affected how it responded to heating. These details matter because they tell us about diversity in the comet population, about the range of properties that these objects can have. The speculation that arose during the observation campaign, the claims of artificial patterns or unusual regularities, will also fade, as speculation always does when it's not supported by evidence. This is part of the public's learning process when it comes to science. Extraordinary claims require extraordinary evidence, and when that evidence isn't forthcoming, the claims get quietly set aside and people move on to the next thing. For researchers who had to spend time addressing those claims, who had to carefully explain why the data didn't support the extraordinary interpretations, it was a distraction but also an opportunity for public education. Explaining why we don't see evidence of anything artificial, why the patterns people thought they were seeing were actually just noise or normal variability, helps the public understand how science distinguishes signal from noise, how we evaluate claims, why skepticism is a crucial part of the process. And let's be clear about something. The desire to find something extraordinary, to discover evidence of intelligence beyond Earth, is completely understandable and even laudable. We should be looking for signs of other civilizations. We should be alert to the possibility that we might encounter something genuinely anomalous that requires new physics or new explanations. But we can't let that desire lead us to see patterns that aren't there or to jump to conclusions without adequate evidence. The universe is full of genuine wonders that don't require appeals to the extraordinary. A naturally occurring interstellar comet, carrying chemistry from another star system, behaving in ways that challenge our models but still fall within the bounds of known physics that's extraordinary enough. That's a genuine marvel that deserves our attention and study. As 3I Atlas fades from view, as it becomes too dim for even professional telescopes to track, it will transition from an object of active observation to an object of historical study. Papers will be published analyzing the data collected during its apparition. PhD students will write dissertations examining specific aspects of its behavior. Models will be refined to account for what we learned, and gradually, 3I Atlas will take its place in the catalogue of interstellar objects, the handful of visitors from beyond our solar system that we've had the opportunity to study. It will be compared with Oumuamua and Borisov, the two interstellar objects discovered before it. Researchers will look for commonalities and differences, trying to understand what's typical for interstellar comets and what's unique to each individual object. The broader significance of studying interstellar objects extends beyond just understanding comets. These visitors tell us about the frequency with which material is ejected from other planetary systems, which in turn tells us about the dynamics of planet formation and the interactions between young planets and the disks of material from which they form. They tell us about the composition of material around other stars, which bears on questions of astrobiology and whether the chemistry necessary for life is common or rare in the galaxy. They give us glimpses, however brief, of the diversity that exists beyond our immediate neighborhood. Every interstellar object is a data point in our emerging understanding of what the galaxy is like, what kinds of systems exist around other stars, how frequently we can expect to encounter visitors from those distant places. Looking forward, we're getting better at detecting interstellar objects as they pass through. Improved survey telescopes, automated detection algorithms, faster communication networks that allow discoveries to be shared globally within hours. All of these advances increase the chances that we'll spot future visitors early enough to mount effective observation campaigns or even, one day, intercept them with spacecraft. The Vera Rubin Observatory, when it comes online, is expected to dramatically increase the detection rate of transient objects, including interstellar visitors. We might go from finding one interstellar object every few years to finding several per year, building up a population that we can study statistically. And if we do reach the point where we can launch intercept missions where we detect an interstellar object early enough and have the technology to send a spacecraft to meet it, the scientific return would be transformative. Direct sampling of material from another star system, laboratory analysis of its composition, imaging of the nucleus at close range, these are the kinds of measurements that would answer questions we can't fully address with remote observations alone. There have been conceptual studies of such missions, designs for spacecraft that could reach high velocities and carry the instrumentation needed to study an interstellar object up close. Whether and when such missions become reality depends on funding, technology development, and political will, but the scientific case is compelling. And the observations of objects like 3I Atlas help make that case by demonstrating how much we can learn and how many questions remain that require closer study. For those of you who have followed the story of 3I Atlas, who have read this far, who have perhaps gone out and observed the comet yourself, or at least followed along with the reports and images, thank you. Thank you for caring about this, for being curious, for wanting to understand what's happening in the sky above us. Science advances not just through the work of professional researchers, but through the engagement of an interested, educated public that values discovery and supports the quest for knowledge. Your attention, your curiosity, your willingness to spend time learning about an obscure comet that most people will never hear about that matters. It's part of what sustains the scientific enterprise, what justifies the resources we devote to studying the cosmos. If you've enjoyed this journey through the mystery of 3I Atlas, if this story of an interstellar visitor's unexpected dimming has captured your imagination, I encourage you to subscribe to this channel, to hit that notification bell so you'll hear about future cosmic stories as they unfold. The universe is endlessly creative in providing new phenomena to study, new puzzles to solve, new opportunities to learn. There will be other interstellar objects, other comets with their own unique behaviors, other mysteries that emerge from the data and demand explanation. I'll be here covering them, exploring them, trying to make sense of them in the same way we've explored 3i Atlas together. And drop your thoughts in the comments. What did you make of this story? Did the dimming make sense to you once the explanations were laid out, or do you think there are still unanswered questions? If you observed 3i Atlas yourself, tell us about your experience. Where were you observing from? What equipment did you use? Did you manage to see the comet, to capture an image, to contribute to the global observation campaign? And more broadly, what do you think about interstellar objects? Are they as fascinating to you as they are to me? Do you hope we'll one day be able to send a mission to intercept one? Let's have that conversation in the comments. Let's build this community of people who look up at the sky and wonder, who want to understand, who refuse to accept easy answers when the universe presents us with genuine mysteries. 3i Atlas is fading into the Leo constellation now, continuing its outbound path, becoming dimmer with each passing night as it recedes from both Earth and Sunday. Professional observatories will track it as long as they can, squeezing out every last bit of data before it becomes too faint to detect. But even after we lose sight of it, even after the last observation is recorded and the last paper published, the comet will continue its journey. It will cross the orbit of Jupiter, then Saturn, then the outer ice giants Neptune and Uranus. Eventually, it will pass the heliopause, the boundary where the sun's influence fades and interstellar space truly begins. And then it will be gone from our solar system, returned to the galaxy, carrying with it whatever changes its brief encounter with our sun produced. But the knowledge remains, the understanding we've gained, the lessons learned about how interstellar comets behave and how our models need to be refined that stays with us. The experience of observing this particular visitor, of tracking its path through our skies, of puzzling over its unexpected dimming that becomes part of our collective memory, part of the story of human exploration of the cosmos. We're living in a remarkable time, an era when we can detect and study visitors from other star systems, when the technology exists to extract meaningful scientific data from objects that spend only weeks or months within range of our instruments. Every interstellar object that passes through is a gift, an opportunity to expand our understanding of the universe beyond our immediate neighborhood. So as 3i Atlas fades into history, as it joins the catalogue of studied objects and becomes a reference point for future discoveries, we can appreciate what it taught us. We can marvel at the fact that something from another stellar system passed through ours, and we were here to witness it, to study it, to add to human knowledge because of it. And we can look forward to the next visitor, to the next interstellar object that will inevitably be discovered, to the next opportunity to peer beyond our cosmic backyard and learn about the vast, diverse, endlessly fascinating universe in which we live. Thank you for being part of this investigation. Thank you for your curiosity, your attention, your willingness to engage with complex scientific questions and follow along as we work toward understanding. The universe is out there, full of wonders and mysteries, and every time we look up with curiosity and determination, every time we refuse to accept ignorance when knowledge is within reach, we add to the grand project of understanding our place in the cosmos. 3i Atlas may be fading, but our quest for knowledge continues, as bright and persistent as ever. Until next time, keep looking up, keep wondering, keep asking questions, because the universe is always ready with new stories to tell, new phenomena to explore, new opportunities to expand the boundaries of what we know. And when that next cosmic mystery appears in our skies, we'll be ready to investigate it together, to unravel its secrets, to add another chapter to humanity's ever-growing understanding of the infinite universe that surrounds us.